Let's talk a little bit about constitutional isomers. Now, these are some of the most underrated practice problems in most organic textbooks. They talk about constitutional isomers but don't go over it a lot. So I have this one separate out for you so you can kind of learn it. It takes a little time, okay, to learn, and I do ask questions about constitutional isomers. So you might as well kind of get comfortable. Okay, so first of all, what are constitutional isomers? Constitutional isomers are compounds that have the same molecular formula but a different structure. So when you have a molecular formula given to you like C4H10, then you can combine them or join them in certain ways which may not have the same structure. Okay, so for example, if you look over here, you can take the 4 carbons and put them in a chain like this. Or you can put 3 carbons in a chain and have one branching out. Now, the main thing here, most important thing here, you cannot change the number of atoms. Okay, they have to still be C4H10. So when you count all the hydrogen out and carbon atoms out, they should still be C4 and 10 hydrogens, right? Four carbons, 10 hydrogens. That's the main thing. And that's the whole definition of constitutional isomers. Same molecular formula, but different structure. The different structure here tells you that they will have different properties also, okay? That's for later. But right now, I want you to understand the importance of this. This is almost like, I say in general, like taking Lego pieces. So if I give you 10 pieces or 14 pieces in which you have 4 blue and let's say 10 yellow, everybody's going to make different things out of it. Okay, that's constitutional isomers because all of you may have the same number of bricks with the same colors, but all of you have different creativity and may come up with different structures. Here also, that's going to happen. Okay, so number one thing is that you have to make sure that you don't lose any carbons or hydrogens. And number two, you want to make sure that you don't violate any rules. That is, you don't violate any octet rules because Lewis structures should be correct. Okay, so you cannot have double bonds, triple bonds when there shouldn't be any, or 5 bonds on carbon. That's not going to happen. Okay, so those are a few things you have to be careful. Other than that, it's really a lot of fun, I feel, drawing out constitutional isomers, depending on your idea of fun. Okay, so these 2 isomers, these were for C4H10. Okay, I wrote the names and you don't have to know the names right now, but I wrote them out just for the fun of it. Okay, so these are 2 different isomers possible for C4. If you added one more carbon to that, made it C5, you would have 3 isomers. If you added one more, you would have 5. C7 would have 9. And you can go on. And you can see that there is no formula for this. Okay, so it's not that if you increase the carbon by 1, you will increase the number of isomers by 1. No, there is no formula following. There is no trend. So which means you just have to write them all out. Okay, so which means that you can have many isomers depending on the type of structure you have or how many carbons you have. So right here, this is what I call many, right? C15, look at that. Who's going to draw all these out, right? So obviously, I'm not going to ask you to draw something like 18 isomers out. It's not going to be possible. So I'm going to say, draw me 5 or something like that. So I'll focus you a little bit on saying how many I need from you. So you don't have to worry about that at least. Okay, in some cases where the molecular formula is small, like for C6, yeah, I can still draw all of the isomers out. Okay, but in some of the cases, I'll have to make it a little bit of a focus. Now, here's another thing. This is hydrocarbon. Okay, but you can also have functional groups in there. Okay, so if you have functional groups, then you are creating even more variations. So then there's definitely, you have to work a little bit harder, okay, in those cases to make sure that you have the right number of, or you've covered all of the isomers, okay, in there. Okay, so that's just the intro. Let's go on. Okay. All of these instructions that I have for you with the general information, this is really just for you to read a lot, okay, here to make sure that you get everything in there. So I tried to write everything out so it's readable and everything has a meaning. Otherwise, I don't write it, okay? You can see that I don't have a textbook of my own. This is my textbook, my PowerPoints, which means that I'm very careful about what I'm writing, okay, in my PowerPoints. Everything I write, it is meaningful, okay? There is no junk in there. Okay, so follow these steps, okay, as we are writing, and then you can make sure that you're doing, you're on the right path. So first of all, the one thing you want to make sure of when you're given a molecular formula is to make sure like you know what kind of hydrocarbon or compound you're dealing with, okay? So which means that you use the formula CnH2n or CnH2n to find out, are you dealing with a saturated compound? Are you dealing with unsaturation, which means are you going to have a double bond or a triple bond? I like to follow the formula CnH2n because this is an easy calculation, right? So just twice the number of carbons and you will know if you have an alkene or not. If you have two more hydrogens, that means you have an alkane. If you have two less hydrogens, you have an alkyne. So this formula is really good to start with. Now, you're also going to have functional groups in there. So if you have a halide, just treat it like hydrogen. Okay, I was talking about that when we dealt with functional groups also. So if you have a chlorine or a bromine or something, just treat it like a hydrogen, which means you can use this formula, okay, for that. Oxygen does not change anything in the formula because oxygen can fit in just, you know, between the two atoms. No problem. So which means the formula doesn't matter at all, okay, for this one. If you have CnH2n, it means that you're still going to have one double bond in there. If you have CnH2n plus 2, it means you're still going to have an alkane. The oxygen is not going to make a difference. Oxygen will make a difference as in what functional group you write. So if you have a double bond, CnH2n, that double bond can be between carbon and carbon, or that double bond can be between carbon and oxygen. Either way, it's fine. Okay. All right. Unless I'm saying, okay, give me the functional groups, you know, blah, blah, blah for this molecular formula. So if I say specifically give me for aldehyde, then you know the double bond is between carbon and oxygen. If I say give me 3 alkenes, then you know it's a carbon-carbon double bond. Okay. So unless I'm specifying, you know, you're open to write whatever you want to. So that's kind of how it works. Now, if you have an amine, it's a little bit different. Okay, so usually I will not ask you to calculate for amines. If you're given a mean molecular formula, just write whatever you want to, provided you don't break any octet rules, okay, in there. You don't have to worry about using this formula, okay, for an amine. So anyhow, as soon as you see that you have an oxygen in the molecular formula, you know that you're going to have an alcohol, ether, aldehyde, or a ketone. You can't have an ester or an acid because those need two oxygens. All right. So, I mean, there are some things, I mean, you have to be really good, first of all, in your functional groups, okay, in order to write good constitutional isomers. So make sure you learn your functional groups really well, okay, when you're doing constitutional isomers. Now, this is not a major part of organic, but this is still an important part, okay, for organic. Okay, a little bit more about how you're going to write constitutional isomers. This is my guideline, and I hope you follow it because one of the things you want to be when you write constitutional isomers is organized. If you're not organized, then you're going to have a little bit of a problem, okay, because you're going to get lost as to which one did you draw. Is it the same as the other one? So it can be confusing. As you will see, I'll go through all of these, okay? So write the isomer systematically, okay? Don't move too many atoms at one time. Be very, you know, organized in how you're moving everything. You're going to get duplicates if you're not careful, all right? So be careful with that. I mentioned to you about single bonds and groups going up and down. they are the same things. Okay, it's very rare, and especially right now, I'm not going to bother you at all about whether groups are going up or down. It doesn't matter. So at this point, don't worry about any of that. Just write your groups, but just know that an alcohol group going up or an alcohol group down or sideways, it's all the same so long it is connected to the same carbon. So connectivity is the important thing. Now, if you move that alcohol group from a first carbon to the second carbon, now you have something different. Okay, so be careful with that kind of a thing. Try to write in line structures. If you keep writing your hydrogens, trust me, you will get a wrong structure somewhere. Okay, because at some point you're going to miss out a hydrogen, and then I will be like, where is this? Okay, because you're missing a hydrogen, you're missing saturation or unsaturation, whatever it is. Okay, so better to get comfortable with the line structures as much as possible. You do have to count your atoms. Okay, so I'll teach you as we go through this that you count your atoms once, and then if you don't change too many things in there, or if you change logically, then you should not get any structure wrong. You should not have to count your carbon and hydrogen atoms every single time. You should not have to do that. Okay, so you have to follow a systematic way, otherwise you're going to be wasting time, okay, in there. And that's what this is about. Okay, is counting the carbon hydrogens just the one time, and that's it. All right. And here another suggestion here is that number your carbons. Okay, so when we were doing what were we doing before? Yeah, just writing line structures, right? So in the line structures also, I wrote out the numbers for you. Okay, so number your carbons. It's really helpful. Okay, you can leave the numbers on there for me if you want to when I'm grading. You know, it's fine. I don't mind. Erase it if you want to, but number your carbons because that's going to help you a lot. Okay, in there. So please follow these general guidelines. Okay, make sure you read through them. Even though I've gone through them, just read through them again to make yourself comfortable. All right, so now let's talk about writing constitutional isomers and the functional groups. If you're given a molecular formula, all right, containing carbon, hydrogen, and oxygen, and you find there is unsaturation in there, there's a double bond. Unsaturation meaning there is a double bond, at least one double bond or maybe a triple bond. You can draw so many isomers from there. Okay, so I have to guide you a little bit, and then I also have to help you a little bit in telling you what can you draw from those. Okay, so if you see that, okay, you have an oxygen in there, but everything is saturated, well, what can you draw from those things? You can definitely draw alcohol, but you can also draw ethers, okay, from there. So if I say that give me 6 constitutional isomers for this small formula, and you're thinking I can get only 3 alcohols, well, maybe there are 3 ethers also possible that you didn't look into. Okay, all right. These are what I call siblings. Okay, so let me go through that. So for example, if you're given a formula for an alkane, well, alkane is just going to be an alkane, no issues. Okay, in there you cannot draw anything else from an alkane, so you can't go to cycloalkane. Okay, because remember, alkane to cycloalkane is a loss of 2 hydrogens. Okay, so you cannot draw cycloalkane from an alkane, so keep an alkane and alkane, that's it. Alkenes and cycloalkanes, they have the same formula because both of them have lost 2 hydrogens from alkanes, so both of those will have the same molecular formula. So which means if you are drawing an alkene, you can also draw cycloalkane. If you're drawing an alkyne, you can also draw cycloalkenes, because going from alkyne to alkene, cycloalkene, you lose 2 more hydrogens. As you went to a ring, you lose 2 hydrogens, right? Okay. Now, this is not that I'm trying to limit you, okay? If you have an alkyne formula, you can draw 2 alkenes. You can draw whatever structure you want, provided it's correct, in the sense that you're not violating any laws, okay? You're fine. I'm open to creativity, okay? All right, if you have an alcohol, you can draw an ether. Aldehydes and ketones also will have the same molecular formula. Carboxylic acids and esters will have the same molecular formula, and all the amines will have the same molecular formula. So which means you can draw anything out. Okay, pretty much. So these are just suggestions for you. You can draw many, many more, as you will see. What I've gone through here is several examples. Okay, so this is not mandatory that you see everything in one sitting. It's not mandatory you do this at all. It's helpful. Okay, but I go through all of these examples just to show you what all you can do for constitutional isomers. So here's a simple one, C5H12. Okay, now I showed you before they can only have so many isomers for C5H12. So I follow the same thing, which means that I figure out, first of all, what do I have? C5H12, is that an alkene, an alkyne, or an alkane? What is it? So here it turns out that it's going to be an alkane, all right? Because I figured out Cn, which is N is 5, and then H2N plus 2, that gives me 2 times 5 plus 2, 12. So it means C5H12 is an alkane, which means no double bonds, no triple bonds, just simply single bonds. So here it is. I numbered my carbons here just to show you, and I think in some other examples also I have numbered my carbons, but you don't have to. If you want to, you can, but you have to eventually get out of it, okay, because you number too many times and it's just waste of time then. So here is what I do, okay, is I will take off one carbon from here and move it, okay, so anywhere else. So this is what I did, okay, is I moved not the first one because I wanted to keep it the 1, 2, 3, 4. So I took off the 5th carbon from here and moved it to the 2nd carbon. Now, you can do the same thing if you flip it, right? So if I take the first carbon from here and put it on 4, I will get this molecule. If you look at these two, they're exactly the same. Okay, so what is the same about them? It's the connectivity. Okay, the connectivity is that on the 2nd carbon, I have a group coming out. I have a carbon coming out. On the 2nd carbon, I have a group coming out. So whether that 2nd carbon is from the left or the right, it doesn't matter. Okay, there is a carbon coming out of the 2nd carbon. Now remember, we are human beings. We number things. Nature does not number anything. What nature is looking at is, okay, on the 2nd carbon, I have a carbon coming out. That's it. Whether that 2nd carbon is from the left side or right side, nature doesn't care because nature doesn't number. Okay, we do. So these two are the same. Then I can also move another carbon and move it down to 2. Okay, so I still have 5 carbons. Now I knew it was an alkane to begin with, so I drew out an alkane chain. I did not count the number of hydrogens because I knew it's an alkane, so I don't have to, because if I draw 5 carbons, I will automatically have the 12 hydrogens. So I didn't bother this time, okay, because it's an alkane. But in some cases, you do have to, count your hydrogens. So which means what? I have only 3 isomers, okay, only 3 constitutional isomers, 1, 2, 3. Now, some of you may draw this, some of you may draw this, and it's fine. And if you think that, okay, maybe I'll draw this one, it is different. No, it's not. It's the same as this. Okay, and by the way, speaking of drawing structures, this is chicken foot. Okay, we don't do chicken feet in organic. It's not a good idea. So try to draw your carbons as far away from each other as possible, giving them good bond angles. It's a tetrahedral. So yeah, sure, you can have a hydrogen here and still be fine. But the thing is, you're not drawing that hydrogen. Okay, so I can't see that tetrahedral. So it kind of looks like awkward. Okay, at this point. So let's not draw those kind of things. Let's try and draw our bonds properly. Okay, so no chicken feet for me, please. Thank you. Okay, let's move on to the next one. So now C5, H10. Now, since we just did the 12 one before, we know that that was an alkane. So this is an alkene because now I have 2 hydrogens less in here. That was C5H12. So that's an alkane. This is an alkene. So alkene, meaning I have to have at least 1 double bond in there. Okay. Cycloalkene, cycloalkane and alkenes have the same formula. Okay, so we are first going to do alkenes, then we'll do cycloalkanes also. So alkene, first of all, go ahead and draw the chain. Now, whether you have the double bond on the first two carbons or the last two carbons, okay, last two carbons or the first two carbons, it doesn't matter. Okay, so long it's there, that's all that matters. Okay, because so long it's there, meaning like so long it's at the end. This is called terminal, right? So I've been using that word before. This is another place where you can see terminal. And then internal would be inside the chain. So whether this is this terminal or this terminal, it doesn't matter. Okay, because you can flip this molecule and it will look just like the first one. So, you know, be careful with that, all right? Those two are not two different isomers. They're exactly the same things. Now, before you move the carbons, I would move the functional group. Okay, that's what I do. So I move the functional group from the first two carbons. So this is, let me erase this one here and put the numbers. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So on the second 1, 2, here is 1, 2. So 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. I am just starting the numbering from closer to the functional group. Okay, it's helpful to do that. Okay, so here what do we see? On the second carbon, we have the double bond. On the second carbon, we have the double bond. So which means these two are also the same. Okay, so even though you might feel like you have moved the double bond, but you really are creating the same thing. Okay, here. So that's the thing about constitutional isomers that you really have to watch out for, is that you don't draw the same thing again and again. That's why you move one thing at a time. Okay, so you move the one double bond one time and that's it. So one isomer here, one isomer here, okay, one here. Now we can move a carbon, because we can't move the double bond anymore, because if I were to take this and I move it down here, which is what I did here, it's the same thing as the first one. Okay, so no point moving that. Okay, I'm not going to write the one. Okay, now I'm going to move a carbon. Okay, so moving the carbon, now I have two isomers, okay, over here. So I have an isomer which looks like this, and I have an isomer that looks like this. So I can move one carbon, this carbon, or I can move this carbon, right? So you have to be careful what carbon you're moving. Again, you can have model sets. I encourage you to have model sets to go ahead and make these models also, if that helps you. So now if you move this carbon from here, you can move it here, you can move it here. All right, this carbon, you can move it here, you can move it here, or you can move it, well, you can't move it there because we have to move one carbon, okay, from there. So which means that you can have a chain of 4 carbons, all right, because if you're going to move a carbon, your chain should be 1, 2, 3, 4 only, because one carbon then is the branch. Okay, so I have moved all the carbons, and you can go through all of these, okay, as you wish, but the first two I have circled because those two are exactly the same. Okay, so here 1, 2, 3, 4. Start the numbering from where the functional group is. So 1, 2, 3, 4. If you follow my guideline, okay, you will see that it will help you later on also. So if I'm telling you right now to number from the functional group, just follow me, okay? Just follow my guideline. Okay. So 1, 2, 3, 4. On the second carbon, I have a carbon. On the second carbon, I have a carbon. So which means these two are the same. Now these two are different because the location of the double bond is different. Okay. So which means what now? It means that instead of having 4 structures, I only actually have 3 structures here. Okay. So one for this, one for 1, 2, 3 structures here. That's it. Okay, now can I move one more? Can I move one more atom? You can try to do that, which means that you need 3 carbons in a chain like this. And then if you're saying I want to move 2 atoms, can you move 2 atoms? You can try, but it's not going to work because now you have 5 bonds on carbon, and that's not going to work. Okay, so be careful with that. You can only move one time in this, or one carbon in this one. You can't move 2 carbons. Okay, so be careful. Okay, and then the rest of the structures that I have for you down here, these are all the cycloalkanes, because cycloalkanes have the same CnH2n formula. Okay, so I started with a 5 carbon structure because I have maximum of 5 carbons in there. So I'll start with 5 carbons. Then I shrunk it down to 4 and had 1 branching. I shrunk it down more to give a triangle, 3 carbons, and then 2 carbons hanging out. And then I just have variations of that. So you can have anything you want. Okay, I've said that before also, and I'll say it again. You can have anything you want, provided that you're not breaking any of the rules. Okay, and the rule specifically is the octet rule. Okay, I don't want to see any 5 bonds on carbons or 3 bonds. And again, you know, so you can see that I'm drawing line structures here, so feel free to draw the line structures. The more hydrogens you draw, the more confusion you have. Have comfort and confidence in your functional groups. Now for the isomers for oxygen. Okay, I'm not going to go through all of them because now you know the fundamentals, okay, of what I'm trying to do. So here, once you go through all of these things, you will see how I have done these. So for example, C5H12O, I calculate the formula, I figure out whether I have saturated or not system. And again, I remember, don't count the oxygen, okay? When you have the oxygens, leave it out of the formula, no problem. So if this is following the alkane formula, which it is, then it means I have all single bonds. If I have all single bonds and I have an oxygen, I have the option of making an alcohol or an ether. Okay, so I'll start with the alcohol. I always move the functional group first. That's my system. Okay, so I move the functional group to the 2nd carbon to the 3rd carbon. If I move once more, it's going to be the 2nd carbon here, which is the same as this one. Okay, so make sure you don't have any duplicates. And then I move 1 carbon. Okay, so now here you want to make sure that you don't have any duplicates from here to here, and hopefully you can see that the last one here is the same as this one. Okay, so let me circle that for you. So this one is the same as this one, even though you were moving carbons, right? You thought, oh, I'm moving carbons happily, but when you move this carbon, now on the 2nd carbon you have an OH, and here on the 2nd carbon you have an OH. Okay, so just don't be happily moving carbons and then forget that you've drawn something before. It can happen. Okay, so it's very common mistake. Again, practice then. Okay, practice. That's all that helps. And then you can move another carbon. So move another one from here, because you've already moved from 5 carbon chain to 4 carbon chain. So now you should have a 1, 2, 3 carbon chain. 1, 2, 3 carbon chain, and then you can move the 2 carbons. Okay, so now you have 2 carbons to move around. So those 2 carbons can be on the first one or they can be on the second one. Okay, as you wish. So I think I'm missing 1 carbon here. Yeah, I should have 1 here. Sorry about that. So 1, 2, 3, 4, 5. Okay, that shall be corrected before I record this, okay, or before I finish this, but anyhow, so I was missing 1 carbon. Always count your carbons, right? That's how it is. So, and I usually do, but I missed out on this one. Okay, so 5 carbons there. And then the next one is then the ethers. Ethers, again, here what I did is I can move, yeah. For straight chains, I mean, you can do whatever you want, right? I should have moved the ether first. Okay, so this one and this one should be written first, you know, together, and I'll do that when I finalize this recording, so that way they're all consistent, and then you can start moving carbons around. Okay, so on one side you can have 1 carbon, on the other side you have 1, 2, 3, 4 carbons. So in that 4 carbon you can start doing the branching then. Okay, Lots of isomers to write out for this one, right? So I have a total of 14 isomers. Now, if you're thinking, oh my God, how do I know there are 14? You don't know until you draw them out. And second of all, will you have to draw all the 14 for me? Absolutely no. I will say draw me 2 alcohols and 2 ethers or something like that, okay? So that way, you don't have to think about drawing all these many isomers, okay? Because it's really tedious, okay, to do that. Okay, so more aldehydes and ketones now and stuff. So here is one for C5H10O, and C5H10O means there is one unsaturation, and you can see how many there are. Okay, I think there were more like 40 or something, I don't know. So that's a lot. Okay, so for C5H10, I have 2 less hydrogens, which means that I can have either a ring or I can have a double bond, okay, in there. So I started with the double bond, moving alcohol, then moving the double bond, moving double bond, moving carbons. And here are the cyclic structures. These are the ethers, okay, with a double bond. Then the other ethers with moving the carbon. Here are the ethers with all the ring structures. So if you have a straight chain ether, you have to have the double bond, okay, because there is 1 degree, there is missing 2 hydrogens here. Okay, and then you can also have aldehydes and ketones, okay, because you need 1 double bond, and aldehydes and ketones will give you that. So that's where this is coming from. You can see, I mean, it's a lot. So for this kind of a question, what can I ask you? I can't ask you to draw all of these. I can say, give me, 3 or 4 different functional groups, okay, for C5H10O, and so you can just pick 1, 2, 3, 4 from here, 5 from here. Not from this slide, I mean like from your creativity. Okay, and here are some acids and esters. So just go through that. Okay, again, let me know if you have any questions or issues, or if I'm missing any carbon. Hopefully I'm not missing any carbons. And I can see that C5 is my favorite. It's not my favorite. It's kind of a good number to handle. If I go C6, then you can see how many more isomers I'm going to have. So all of these isomers that I've dealt with here, these are all C5s or C4s, and it's a little bit more manageable. Okay. So here I have the acids and here I have the esters. Go ahead and either draw them on your own, or, and then check your answers, or just go through these and see how I've made these isomers. Okay, and then finally for amines. Okay, amines are a little bit different because you can have 3 different kinds of amines: primary, secondary, and tertiary. So first of all, like, how do you know if it's going to be straight chain or cyclic? Okay, so the best thing to do for an amine is to go ahead and draw at least a simple one out. Okay, there is a formula you can use, but I'm not going to do that because there is so much more to do anyway. So C5H13N. So go ahead and draw 5 carbons out, draw the nitrogen out, put, and then count all your hydrogens, okay, in there. How do you count your hydrogens? Very simply, you have 3 hydrogens here because there is 1 bond. You have 2 hydrogens here because there's 2 bonds, 2 here, 2 here, 2 here, and then 2 here, right? So 1, 2, 3, 4, 5, that's 10, and 3, 13. Okay, so you have 13 hydrogens, which means your structure is fine. If you form a ring, you're going to lose 2 of those hydrogens. Okay, so don't form a ring, just keep it to be a straight chain, and you don't have to count your hydrogens again. Okay, so if you don't change the bonds, which means go from a single bond to a double bond, or go from a straight chain to a ring, you don't have to count your hydrogens again, because that's when you change the hydrogens. Okay. So here you are going to learn something new, okay, and that something new is primary, secondary, and tertiary, which is also written as primary, secondary, and tertiary. So a primary, second, tertiary will become really important for us. So even now it's going to be important, and later on in a few chapters we'll talk about it again, actually in chapter 4. Okay, so a primary amine is when you have the nitrogen connected to 1 carbon. That's a primary amine. A secondary amine is when the nitrogen is connected to 2 carbons. Okay, so it's internal. Now it's moved to the middle. A tertiary amine, yeah, you guessed it, it's connected to 3 carbons. That's it. That's primary, secondary, and tertiary for us, okay? That's really how we do primary, secondary, and tertiary. So even if I'm asking you to draw me a primary alcohol, a primary alcohol is an alcohol that is connected to one carbon. Now, one carbon is always going to be connected to, but that carbon is connected to one carbon. That's a primary alcohol, or a halide. It's all about connectivity, okay? What is the connection like? So that one carbon that this group is connected to, how many carbons is that connected to? Because that group is going to be connected to one carbon always, right? So it's about how many other carbons there are. So this alcohol is connected to one carbon, which is connected to two carbons. So that's a secondary alcohol, okay? Right now we'll focus a lot more on the amines, okay? So hopefully you won't see too many of the alcohols and halides, but if you do, that's where it's coming from, okay? But anyhow, so amines, you can draw primary, secondary, and tertiary with this formula, okay? So here are the primary amines. What have I done? I have taken the NH2 and then moved it around so you can clearly see the NH2, all right? So if I move it once more, it will be the same as this. And then I took the primary amine, this structure, and I moved the carbon once, then I moved it again, then I moved two carbons, right? So you can see how it's going, all right? Then I took this one structure, and then I moved one more carbon. So, you know, you just keep drawing new structures out. That's all it is. Secondary amine is when you put the amine in the middle of two carbons and then try to move the number of carbons. And tertiary would be when you have the nitrogen in between three carbons, and then keep moving carbons. That's it. So it just takes a little practice. It takes a little creativity. I always say that, you know, this is something you can do while you're watching TV, but I'm not going to say that because sometimes you need to concentrate also, okay, and focus on what you're doing and make sure you don't repeat any structures. You will see that I have line structures here also, and I prefer line structures, okay, to any other kind. So I think that's it, okay, for this one. Just again to emphasize, you know, you have to know your functional groups, okay, before you start doing this, because the more comfortable you are with the functional groups, the better you will be at constitutional isomers also.